my great pleasure to introduce the first speaker this morning, George P.H. Styan. George was conceived in Danzig, born in England, studied in the Sorbonne, University of Birmingham, and Oxford, immigrated to the United States, to Cincinnati, studied statistics, mathematical statistics at Columbia University. I met George when we both were young assistant professors at the University of Minnesota. From there he moved to McGill and has been on the move ever since, in the best possible sense. To show just how far George has come in the world of statistics, whereas Professor Anderson. I understand that when George was a new graduate student at Columbia, he went to Professor Anderson. He was enrolled in his multivariate analysis class, and made an appointment to ask which textbook did Professor Anderson intend to use in his course. George has come a long way.
I wonder who you had breakfast with today.
George will speak to us today on partially ordered idempotent matrices.
Thank you very much, Michael. Well, after that introduction, I think I should say a few words of thanks to various people. I was challenged yesterday at dinner by Professor Anderson that I should say some thank you words in Finnish. Unfortunately, it is not I, but my wife who's taking the Finnish course this week, so my Finnish is limited. But I would like to say a profound thank you to the organizers of this conference, not only for inviting me, but for having organized a superb conference, one that is a benchmark against which other conferences should be measured. Particular thanks to Tarmo Pukila and Simo Puntanen. And I think that this is for the people who didn't understand the Swedish that was said yesterday. Now, I have to make sure that I don't stand in the way, and I might possibly use this. The work I'm going to talk about is not really in statistics, but since almost everyone in the list of references is here, there must be something of interest, I suppose, in matrices for a number of you. In particular, one person who is not here is my co-author, Robert Hartwig, who is spending the summer in the bucolic part of southwestern Austria. It was hoped that he might come, but was not able to come. And some closely related work is with Hergé, Baxalary, and Friedrich Puckelsheim. In fact, the opportunity that was afforded here for the three of us to meet allowed us to finish a paper yesterday at approximately 5 o'clock before we retired to an appropriate watering hole. We're going to talk, or I'm going to talk about partially ordered idempotent matrices. They don't actually look like that, though that, I suppose, is a partially ordered sequence. I'm going to talk about matrices which are possibly rectangular, possibly square. Sometimes they will be Hermitian. They'll have elements which are complex numbers, but the motivation really is for matrices with real numbers as the entries. And I'll be interested in a matrix B that might lie above in some partial ordering, an idempotent matrix A that might lie below an idempotent matrix B, or I might make both A and B idempotent, and then look for characterizations connecting A and B. I will use this symbol for the ordering, a less than or equal to sign, which I will embellish with an appropriate symbol, which we will define in a moment. A matrix partial ordering must satisfy a pre-ordering condition, so that if A is less than B and B is less than C, then A is less than C. And an antisymmetric kind of relationship whereby if A is less than B and B is less than A, then A is equal to B. The most well-known, and I guess the most used matrix partial ordering in statistics is the Louvin ordering, And Friedrich and I have been debating for the last 24 hours whether there should be an umlaut on top of the O, and he has promised to both listen to me for the next few minutes and to work out the solution to that. So by 10:30 we hope to have the end of my lecture and the answer to the umlaut question. Two matrices A and B are ordered according to the Louvin ordering if the difference B minus A is Hermitian non-negative definite, which may be defined by just writing it in the form RR star, where star denotes conjugate transpose. The quantity in the middle there, little p, may or may not be the rank. It will, of course, have to be greater than or equal to the rank of that difference. Something which statisticians, I think, have never considered before are matrices that are so ordered by the Louvin ordering, but which are themselves not necessarily Hermitian or symmetric. It was something that was suggested to me by Robert Hartwig, and I had not noticed that generalization before. Another matrix partial ordering is the Drazen ordering, which was proposed in 1978, so considerably after the Louvin one, 44 years earlier. We'll write A less than B in the star ordering if these two conditions are satisfied. These have to do then with the Gramians A star A and A star being respectively A star B and B A star. I'll put a star there and I'll put an L there. In our joint work, Robert and I have consistently used the less than or equal sign without any embellishment, and neither of us know what it means, and so I've now put an embellishment on all three of these orderings, the ones that I'm going to consider. And the third one is the rank subtractive ordering, and it was shown by Hartwig in 1980 that this ordering is indeed a matrix partial ordering, that is, it satisfies A and B, and rank subtractive I'll abbreviate with RS below it. So each of these three will have an embellishment. In the abstract and in the final paper, using the excellent computing facilities here, I hope to have three distinct symbols that will involve wiggles or little things embedded in other things and so on. But for the purposes of today's lecture, I'll use L star and RS. So the RS, or rank subtractive order, is just that the rank of the difference is the difference of the ranks. This was originally called the plus order by Hartwig, when I pointed out to him that a matrix to the plus is often the Moore-Penrose inverse, as for example in C.R. Rao's book, though among mathematicians they use a dagger. He changed it to the minus order, and since I can't ever remember whether it's the plus or the minus order, I'll just refer to it as the rank subtractive order. I don't think I need that. Just to show you that there is some statistics involved, if we're comparing two estimators of a vector beta, let's call them beta hat and beta star, then we may conclude that beta hat is better than beta star if the covariance matrix of beta hat is less than that of beta star in the Louvin ordering. That equivalently means that the quadratic form L prime sigma hat L is less than or equal to the quadratic form L prime sigma star L for all possible column vectors L. This then is the regular less than or equal to, because these things on the left and on the right are scalars. And indeed, the Gauss-Markov theorem says that the ordinary least squares estimator is blue in the general linear model with white noise. And that is that uses the Louvin ordering, whereby beta hat is any what I call Louis, a linear unbiased estimator, and with the other way around. Beta hat will be the least squares estimator, and beta star will be an arbitrary linear unbiased estimator. Another area of statistics where these orderings play a role is that of Chisquaredness. The well-known Cochrans theorem that I think appears in essentially every book on regression analysis or the analysis of variance says in effect that if E is less than F in the rank subtractive ordering, and if F is idempotent, then E is idempotent and F minus E is idempotent. These matrices, in fact, need not be symmetric for this result to hold, and I think that that was first shown by Khatri in 1968 that the symmetry could be removed there. In the statistical context, this means that if you make both E and F symmetric, and if they are ordered according to the rank subtractive ordering, and if the bigger one is chi-squared, then the smaller one is chi-squared, and the difference is chi-squared. There's additional work by Khatri more recently on idempotent matrices, which I've enjoyed reading. The original theorem, Cochrans, is 1934. There's a paper by Chipman and Rao, which did some early work in removing the symmetry from this result. And there's a survey in the Festschrift for C.R. Rao by Professor Ted Anderson and myself in 1982. Another result involving chi-squared, which is, I think, considerably less well known, in matrix terms says that if both E and F are idempotent, usually taken to be symmetric or Hermitian, but in this result they do not have to be, and if they are ordered by the Louvin ordering, then the difference is also idempotent. What this means in statistics is that if you have a random vector x, components of which are IID normal 0, 1, and if x prime ex and x prime fx are chi-squared, which is what is implied by the idempotence, and if you have that one is less than or equal to the other with the ordinary less than or equal to sign, and if the rank is such that one is strictly less than the other in rank so that the difference is positive, then the difference is also chi-squared. That, I believe, was first established by Ogasawara and Takahashi in 1951, but is often called Hogan-Craig's theorem, published in the Annals in 1958. The reference to Ogasawara and Takahashi is in the Journal of the Hiroshima University section on science, which was a reference that was a little harder to obtain, and I'm very grateful to Professor Anderson for having given me that reference. More recently, when I was on sabbatical in Finland in 1975-76, Timo Mekalainen and I slightly generalized this result, taking the Louvin ordering away and using only that the matrix F minus E has to have index 1, or that the rank of the square is the rank of itself, and that the eigenvalues be non-negative definite. It occurred to me last night that this might or might not be a matrix partial ordering. Hergé is wonderful at producing counterexamples, so you can probably immediately give me a counterexample that it's not a matrix partial ordering. The Louvin ordering, as we defined earlier, is that the difference between these two matrices B and A is such that they can be written in this Gramian form, RR star, can be characterized by the difference being Hermitian and all the eigenvalues being non-negative. I had some difficulty with the notation here with my co-author, who thought that CH implied cheese, and he didn't think that cheese was appropriate in a paper on mathematics. But I was trained by Anderson, worked with Perlman, and various others who used this notation, so I told him that I couldn't possibly not use that notation here. And as we saw earlier, another characterization is that the matrix be Hermitian, the difference be Hermitian, and that the quadratic forms satisfy the usual ordering. So here are some more references. The earlier reference by Louvin, which is sitting on my left on Friedrich's desk. The book on linear statistical inference by Rao has considerable number of results on the Louvin ordering, as does the book by Marshall and Alkin. And there's a survey by Gafka and Kraft in a rather obscure, I think, proceedings volume, which is not readily known, but I can give anybody the reference to this and anything else as they might wish. The Drazen ordering may be characterized by a simultaneous singular value decomposition, as illustrated here, so that the unitary matrices U and V, that represent, if you like, the singular vectors, or the eigenvectors of A star A and AA star, appear both for B and for A, and where the singular values are exhibited in these diagonal matrices, and such that every non-zero singular value of A is also a singular value of B, but there may be a few extras in B. There's the definition, U and V unitary. the 2D's diagonal positive definite, and on the diagonal are the singular values, and we'll assume that B is greater than A, though of course the case of B equal to A works as well, but then D is 0, and hence not positive definite. Hartwig and I proved in a paper last year that the star ordering is equivalent to the rank subtractive ordering and a dagger subtractive property of this type. Because Hartwig used plus for something else, we are now using daggers, but the way we both write, it doesn't really make much difference. Related work a long time ago by Magnus Hestenes was not really in the partial ordering area, but contains a number of closely related results. There's an earlier paper by Hartwig, our joint paper, and the original paper by Dresen. The rank subtractive ordering, basic definition, formerly known as the minus and plus order, may be characterized by any one of these three. That a generalized inverse of B be also a generalized inverse of A in the sense of Rao, that B also have its columns, that A also have its columns and its rows in the row and column space of B. And then there's another one there involving generalized inverses and another one there involving generalized inverses. If these are true for any one generalized inverse, then they will all be true for every generalized inverse. Those characterizations appear in a paper by Marcelia and myself 13 years ago. The rank of a difference was treated quite extensively in an mainly expository paper by Klein and Funderlich in 1979, and some related work by Hartwig, Beck-Salary, and a series of co-authors, and I didn't quite have room for all of Beck-Salary's papers. I think there are some others, and didn't quite get those in there. And there's a very recent paper by Sujit Kumar Mitra, who I guess is one of the matrix connoisseurs who has done a lot of work in this area and who is not present. A question then arises as to which of these three orders is the strongest, which is the weakest. As we saw earlier, the star ordering always implies the rank subtractive ordering. If the two matrices G and H are both Hermitian, and if the bigger one is non-negative definite, then you get this relationship, which makes the Louvin ordering the weakest. So here the Dresen ordering is the strongest, the rank subtractive one in the middle, this always implies this, and the Louvin ordering is the weakest. For this result, G and H are Hermitian, H non-negative definite. I'm talking today about idempotent matrices. If E and F are idempotent with neither necessarily Hermitian, then the Louvin ordering turns out to be the strongest. It implies the star ordering, which in turn implies the rank subtractive ordering. So if you make these idempotent matrices Hermitian, they become non-negative definite, and the three orderings coincide. So if you are writing a paper on partially ordered Hermitian idempotent matrices, it'll be considerably shorter than if you allow the matrices not necessarily to be Hermitian. That might be a blessing for some people, but not for the real matrix connoisseur. If E and F are both idempotent and Hermitian, often called orthogonal projections, though I find that term not always to be defined in that way, but often certainly defined in that way, then as we have seen, all of the three partial orderings coincide. And if we take then two such matrices, E and F, both idempotent and Hermitian, then this can be characterized by a very nice result that F be a generalized inverse of E, in the sense of Rao, the first Penrose condition, or that the rank of the difference be the rank of this difference and the rank of this difference, or that E be equal to EF or be equal to FE. And I think we have about 14 other conditions, which I will not bore you with today, represented by those three dots. And I found a sentence in a paper by Rao and Yanai that indicated that G inverses play an important role in the discussion of projection operators, And I wonder whether this does in fact appear in Rao's book, and I don't see him here, but I assume he is here. I look forward to hearing from you as to whether you had that in mind or something else in due course. As I said at the beginning, I wondered what lies above and what lies below. What lies below a matrix F that's idempotent and not necessarily Hermitian. If A is less than F in the star ordering, then A must be idempotent. If A lies below F in the rank subtractive ordering, then it must also be idempotent. That's Cochrans' theorem, and since this implies this, you can go this way. However, if A is less than F in the Louvin ordering, and neither is necessarily Hermitian, then the implication need not hold, and here is a simple example where you have a matrix A which is nilpotent and hence not idempotent, which is dominated by this matrix which is idempotent but not Hermitian in the Louvin ordering. The difference is non-negative definite, and indeed it is idempotent. If you make the matrix F that sits above both idempotent and Hermitian, so it becomes an orthogonal projection, then the star ordering is sufficiently strong to give you that same property for A. If F is idempotent and Hermitian and is bigger than A in the star ordering, then A is also idempotent and Hermitian, and we wonder whether the Hermitianness of this result might be new. If, however, it's just rank subtractive, you don't get the Hermitianness, suppose that is a word, and if you have it less than F in the Louvin ordering, then you don't necessarily get the idempotence. There is a quick, really one-line proof of the first result, and here is a counterexample to show that this does not necessarily hold, and here is a counterexample to show that this does not necessarily hold. When I was in the audience the last few days, I got disappointed that I didn't get to see the slides longer on the projector. But I notice I have 6 minutes left and I'm at slide 10, so I'll let you be the way I was. If you put the bigger one equal to the identity, which is certainly Hermitian and certainly idempotent, then a matrix A is less than I in the star ordering, if and only if it is Hermitian idempotent. And so then you get a whole bunch of characterizations of idempotent Hermitian matrices, which are well known. In fact, one reference that I just thought of, which I didn't mention, is the book by Graybill, which has a fairly substantial section on idempotent matrices. These characterizations, however, we have attempted to put in terms of the other orderings, and the Louvin one is the weakest here, and so you've got to add something to it. You've either got to make the difference idempotent or the eigenvalue 0 or 1, or some such condition. If A is less than I in the rank subtractive ordering, then, as we've seen from Cochrans' theorem, that characterizes the matrix A to be idempotent, not necessarily Hermitian, and here we have again some characterizations in terms of the other orderings. Again, the Louvin one is the weakest. You need to add something else. What lies above? Almost everything. One can, however, offer this characterization that if you take a Hermitian idempotent matrix E, and B is bigger than it in the star ordering, then B must commute with it, and the product must give you back E. The rank subtractive ordering, if E is idempotent and not necessarily Hermitian, less than B in the rank subtractive ordering, then you get this probably rather useless characterization. And this, I guess, is sort of a trivial characterization of a matrix B that lies above a Hermitian idempotent matrix in the Louvin ordering. I think that's not terribly exciting, and neither is that. And in fact, there's very little you can say about what lies above. If you make them both idempotent, then you get a little bit more. And indeed, We have a few extra slides here for which I'm sure you'll be happy to know there will not be enough time, but I can give an additional performance on the bus maybe. I think it was very well equipped. At least it had a microwave oven. I don't know if it has a projector, but never mind. I have a Xerox copy of these. I have at least 6 characterizations of this when they're both idempotent, at least 7 of this when they're both idempotent, and at least 6 of this. And then I can do the same as the above with F also Hermitian, and I can do the same with E also Hermitian and F not necessarily Hermitian, and then I can make them both Hermitian, and I can show you the remaining 7 slides at a later time. But I think that this is probably as good a time as any to stop. Quitting while you're ahead, I think, is always a wise move. Thank you very much.